Hello everyone and welcome back to a new video in our introduction to the finite element method, in which we are going to be continuing talking about the isoparametric formulation. Now, for those of you who are new to this channel, please notice that this video is part of a video series which I will be linking on the top right. And of course, this is basically the third part of chapter 10, so please double check the first two parts before you continue, because it kind of builds upon those parts. Now, without further ado, let's dive into it, so sit back, relax, and enjoy the show. Alright, so a quick rundown to what we know so far. We know so far that there is something called the isoparametric formulation, in which we are going to try to take a real quad and basically project it back and forth into a perfect or natural quad. And of course, here you have the real coordinate system with x in the x-axis and y in the y-axis, with their corresponding degrees of freedom u and v. Of course, you're projecting it back and forth to a natural or fantasy coordinate system, where you have this being the S and this being the T. I think there is also books that call it Xi and Eta, but I'm going to use SMT because this is what the book Daryl and Logan says. Now, to do that, we need to connect the real position, i.e. the positions on the real quad, back and forth to the position on the natural perfect square. And of course, this is done by this. So the x position on the real quad is a function in the S and T, which are the coordinates on the natural square, similarly the y. So in short, x is a function in S and T, and y is a function again in S and T. Similarly, I'm going to connect the u using the S and T coordinates, so that is again projection and back projection with regard not only to the coordinates but also to the displacement or degrees of freedom. So now we have x as a function of S and T, y as a function of S and T, u as a function of S and T, and v as a function of S and T. So how do we continue? Well, we need to find strains, because remember, we're going to triple integrate, because this is how the finite element method works. B, I think it was transpose with material matrix D and another B and a bunch of stuff here. So we need the strains, because B is basically the displacement to strain matrix. Now, this is a long story. You should check out my video series. But just to understand, one part or one step in the formulation of the stiffness matrix is to find the strain matrix, which means I need to find the derivative of u with respect to x, partial, derivative of u with respect to y, partial derivative v with respect to x and with respect to y. Now, I explained before that we are going to use the chain rule, because I want to extract from the chain rule this partial x and partial y. This is a very important video. I will be linking it on the top right. This is extremely important and one of the make or break points of chapter 10 if you try to study it yourself. So the previous video is like one very important video, as well as this one, because those two videos are dealing with the most confusing points with regard to chapter 10, so it's really important that you check it out, and you might even have to read it multiple times. Now, I want to find partial x and partial y. This is a two equation with two unknown system, which I can find out by the Kramer's rule or any possible calculation, which means that the partial derivative with respect to x and partial derivative with respect to y is found by this. Now, just to remind you of the previous video, why am I doing the chain rule? I'm doing the chain rule because I try to find things that are with respect to x and respect to y somehow indirectly. And this is what happens. In other words, I can partial derive u with respect to x by using this basic equation. If you replace f with u, you get partial derivative u with a partial derivative to x, which equals every f here being replaced with u. Why do we need partial derivative u to partial derivative x, you ask? Well, because we need to find the strains. Now, we need not only to find partial u to partial x, we need to find partial u to partial x, partial u to partial y, partial vx, vy. It's a long story. If you consider Jacobian matrix or Jacobi matrix, if you consider this thing, the matrix, not the determinant, being the Jacobi, then you can basically simplify by saying, well, this divided by the Jacobi. Like what you see here is the determinant of the top side. What is the determinant of the top side? The determinant of the top side is the main diagonal minus the secondary diagonal. So you have partial f with respect to x multiplied by partial y with respect to t. I don't know why it's sorted like that, but I mean, you get the idea. Now you need to divide this by this stuff, which is the determinant of the Jacobi matrix. So what you see here is basically the calculation of that stuff. We now know, and this is all topic of previous video, and please double check that if you still don't remember that. This is very important. And I need you to be on the same page with me right now. So what I'm saying is you can find the partial derivative of any function with respect to x, because the function here is actually a function of s and t, yet you can somehow find the derivative with respect to x by following this long story. So please double check the previous videos just in case. Of course, our objective here is to find partial u to partial x, partial u to partial y, basically this entire team of partial derivatives. Now to do that, I'm going to show you partial u to partial x and try to understand this and also partial u to partial y. Please notice that the book is somehow cryptic. When it does that, it just jumps over and tells you, hey, you know what? This is the thing you need. But I'm gonna deal with it mathematically step by step. What is partial u to partial x? Well, we need to find this, right? Now, the idea here is we don't apply u directly. What we do is we use the shape functions to approximate u. Remember, u is the displacement field, and we use the shape functions, or the mixing functions, to approximate the displacement field by mixing different percentages of the node displacements. So I can basically replace u by saying summation and I ui. Of course, I have 4 shape functions and 4 u's. Now, if you want to partial derive u with respect to x, this means you need to partial derive the entire summation. For some reason, I'm writing y here, but I actually mean is x. So I think I messed up here, or the teaching assistant messed up. So this is partial to x. Since I want to find the derivative of u with respect to x, this means I have to partial derive this, or I can partial derive this, something that I'm doing here. Now, since I'm partial deriving u with respect to x, which is a summation, this means that the partial derivative enters into the summation. What I mean is partial u with respect to x equals partial, and now we need to do the summation. So I'm using pseudo math here just for understanding. I mean, I know some of you are like mathematics nerds. I'm one of them, but I want to use pseudo math. It might be even accurate sometimes. I want to use pseudo math for your understanding, because my point is that you should understand what we are doing. If you want the entire science of it, you have the reference to check. So we want to partial derive u with respect to x, and we're going to replace u with the summation. Now, since I'm partial deriving a summation with respect to x, you have to partial derive, and this is pseudo mathematics, you have to partial derive each element inside the summation. If you're summing up 4 n's, you need to partial derive each n. Since we are partial deriving each n, well, I will have to use this as my partial derivative. Because I want to partial derive n with respect to x, unfortunately, my n, as we will see later, is a function in s and t, so I need to use the chain rule, the thing I showed you here. I need to use the chain rule to find partial n with respect to x. Now, in that case, of course, I have partial n1, for example, with respect to x, which means this entire thing in n1. Well, turns out this is exactly what I'm doing. This term in red is actually the derivative when you replace this brackets with n1. Now, please notice that it's a summation with 4 n's, so I need to do this replacement 4 times. 1 time for n1, 1 time for n2, 1 time for n3, and 1 time for n4. You know why? Because I'm going to partial derive n1 with respect to x, and then n2 with respect to x, and then n3 with respect to x, and then n4 with respect to x. Of course, they are multiplied by u, so on the outside, there is a u vector that I missed to write here. Of course, remember, this is pseudo math, so me missing some of those values is, well, okayish. What I'm saying is, since u is summation of shape functions, and I want to partial derive it, I have to partial derive each shape function. The shape function is a function in s and t, which means I need to use this big thing to partial derive, which I have done for each one of those n's successfully. Similarly, for u with respect to y, now of course, for u with respect to y, I'm going to use this big derivative, which means I have here partial derivative to t, And once again, I'm applying this 4 times for each one of those shape functions. This is a big thing that tries to find the partial derivative u with respect to x, partial derivative u with respect to y, partial derivative v with respect to x, partial derivative v with respect to y. V with respect to x is very similar to u with respect to x, so, well, that's that. Remember, because u is a summation, when you partial derive it, you have to partial derive the elements in the summation. Because v is a summation, when you partial derive it, you have to partial derive the elements in the summation. The cool thing is, because I'm using similar shape functions, I can basically just copy and paste that stuff. So calculations for the computer is actually minimal. I know I'm messing some things up. For example, here there should be a transpose, and here there should be a determinant. But remember, I'm using pseudo-math this time. So not real math, however, math-esque or math-like logic to try to convey to you the message. Because if you want to have perfect math, you can double-check the book and basically drown in its complexity. So I have my u and etc. What remains now is to find the strain. If you remember, the strain is, well, the B matrix multiplied by the displacement matrix. Now, if I remember correctly, the strain matrix itself was equal to partial derivative u with respect to x and partial derivative v with respect to y, and then the cross partials, like addition. You take u with respect to y, and you take v with respect to x. I call this cross partialing or something. So how do I find partial u with respect to x? Well, we have just done that. This is partial u with respect to x. Notice, partial u with respect to x is multiplied by the u's. So, of course, I need to make partial u with respect to x, which is summation. And I need to keep zeros here because our displacement vector is u, v. So something, nothing, something, nothing, and so on. Because this gets multiplied by u1, as it should be. This gets multiplied by v1, and that's why it's 0, as it should be, and so on. Notice, because I have 4 shape functions from n1 all the way until n4, I would have to do this 4 times. I would have to find partial n1 with respect to x and partial n1 with respect to y, because that's for the partial v with respect to y. And then I would have to find n with respect to y, because this is u with respect to y. And then with respect to x, because that's v with respect to x. The gaps here is because, remember, my displacement function is u1, v1, u2, v2. So I need to multiply this by the u's, because that's epsilon x, this not, and so on. It's kind of cool if you get it. This is like a step-by-step explanation of what you see in the book. Trust me, it might be confusing, but it's way easier than following the book. What I suggest you to do is that you listen to this lecture, and it's 100% fine if you did not get it in the first run. Trust me, it took me some time to understand that. So check out this lecture video, or this video lecture, then go check out the book, read it, and then come back to this video lecture and listen to it again. In the second time after you read the book, when you listen to this video lecture, I think it will make sense. This is one very complicated topic, and the best way is to take a pencil and a pen, a pencil or a pen, and a piece of paper, and jot down those equations yourself. It's really rewarding when you get it right. Of course, here, just to understand, I color-coded that because, remember, our epsilon is partial u with respect to x. I'm just repeating that. And partial v with respect to y. And then partial u with respect to y. This is the shear. Plus partial v with respect to x. Right? So this is u with respect to x. I'm taking the shape function of number 1, putting it here. This is u with respect to y. And I need this for the cross here. This is v with respect to x. I need it for the cross derivative here. And this is v with respect to y. I need it for strain y. This is only for shape function 1. You have to rinse and repeat for shape function 2, and rinse and repeat for 3, and rinse and repeat for 4. It's not fun, but it's very easy to be programmed. And that is the point. Okay, now we've covered that. Now it's time to double check the book and see what the book is doing. Well, the book, being the book, is as cryptic as ever. It defines you a operator matrix. Basically, I will call it the integration matrix. And then tells you, hey, you want to find B? It's the operator matrix multiplied by the shape functions. What he's doing is basically doing this in a more mathematically fancy way. It explains to you that you have B1, B2, B3, and B4 because you have 4 shape functions. And then tells you BI, which could be 1, 2, 3, 4, equals this stuff. Now, I just want to take a minute from you and try to explain to you how this, for N1, translates into this. So let's take a look on that. I am convinced that B1 is going to translate to the color code here. Well, what do we know? Let's check that out. Now, first of all, there is an A here, which is what I think corresponds to this. I think that this partial y to t corresponds to the A. That's my take on it. And then there is NIS. This means partial derivative NI with respect to S. In our case, it's N1 respect to S. And you can see that you see it here. Partial derivative N1 with S. Perfect. There is a negative here, and you can see it here. B is your partial y with S. And you can see it repeating. Look, this is partial y with S. It's actually mentioned here, and you can see the B again. Similarly, this A is partial y with T, and you can see it repeated here, and that's why you see an A here. So I think you're convinced now that what you see here for N1 is actually what happens for B1. Well, duh, I mean, this is B, and this would be B1, one block in the big B matrix, because you're going to have to repeat this for N1, N2, N3, N4. And truth to be said, personally, when I was programming the entire finite elements method, I used this. But of course, that's only a personal opinion. If you feel that you want to use this, be my guest. Now, A seems to be partial y with T. Now, you could derive it, or you could just use the book. The book gives you the A and B and C and D and so on. It's even faster. And I have not said anything about the shape functions, but the shape functions are those. You could call foul here and say, are those shape functions following the Pascal triangle? Well, yes, they are. Because the Pascal triangle says 1, x, y, and then x square, if you remember, xy, and y square. This is the Pascal triangle. I think it was in the linear strain triangle lecture. I'm not sure. Well, the number of terms you try to take is the number of degrees of freedom. If you have 4, you're going to use those terms. Now, in our case, we have S and T, so it's going to be 1, S, T, and ST. Does this produce it? Well, the answer is yes. If you expand those two brackets, you will get a number. It's actually 1. I mean, this expansion will actually yield to 1 minus S minus T plus ST. And you can see that this follows the Pascal triangle. So yeah, those are valid shape functions. Why are they assumed like this? Well, you can double check the book Daryl and Logan. Of course, there is a 4 here. Don't forget about that. I somehow missed it, but there we go. What about the Jacobi matrix? Well, you had the equation. You can use it, or you can just use the book's equation. It's kind of interesting and cool, and we need to see this in action. Now, there are some recommended readings I want to tell you, and some points I want to finalize with. You see, we have our stiffness matrix, which equals B transpose, material matrix, and B H dx dy. Now, this is a problem because my B matrix is, well, as you guessed it, in S and T. So I need to convert dx dy to ds dt. How do I do this? With the Jacobi matrix. This is derived in the book. You can flip the integration of dx dy to integration ds dt with a Jacobi matrix. So now I can actually integrate with respect to S and T because my B is a function in S and T, and we know that S is from -1 to 1 and T is from -1 to 1. This is exactly the reason why we use isoparametric formulation, because this is 100 times easier for evaluation. For numerical integration, you can use Newton cotes or Gauss quadrature. More on that in the next video. But before I reach the next video, I have some recommended reading for you. Well, The next time we are going to use numerical integration, Newton cotes and Gauss quadrature. While we are doing that, you could just check out the body forces and the surface forces and try to remember that the work of the nodal forces should equal the work of the body forces. This is something we explained before, so double check that and tell me what you think about this. I hope you enjoyed the video. Of course, there might be a lot of questions, so feel free to ask them in the comment section. I'm actually really active in that. Usually you will get an answer within 24 hours, maximum 2 days. But, well, feel free to ask anything you want in the quant section. Now, before I finish, I want to give a huge, whopping Newton Cotes Science shout out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as the support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. Of course, I hope that you enjoyed the video and that you found it beneficial, and if you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing as a sacrifice to the YouTube algorithm overlords. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.